Henry Ford first invented this assembly line in 1922. It's been 100 years, and it's really hard to make a change after 100 years. And when you watch it happen, it's actually really silly to a guy like me. You take all these stamp panels, you put them together, then you put them in a framing station, you build a body that looks something like a car, you put the doors on, and then you paint them. Once you get the color, you take the doors off, and then you start putting the interior inside the car. It comes in through the openings that already exist. I wish it went in like this big piece like this, but there's actually people coming in and out of the car. There's awkward movements. Then we lift the car up. We put stuff from underneath it. We put it down. Then we put the seats in the car. And finally, we close it all out with glass, and we bring those doors that went away for a trip, and we put them back in the car. Most of the time, we're doing this with a big, giant car and moving it and doing really nothing to it at all.
What's funny, though, in this kind of whole process is that just recently Toyota just called this an engineering work of art.
True.
The Model Y.
That was humbling, but at Tesla, it's not good enough. If we're going to scale the way we want to do, we have to rethink manufacturing again. As part of the master plan, we have to make another step change in cost. We started this on Model Y when we made these huge gigacastings. And we deleted hundreds of parts. We simplified assembly with the Model Y structural battery, where we decided the floor should be a part of the car. The battery is the floor. We put the seats and the interior on the battery, and we bring it up through a big open hole, and we assemble it. And this allowed us to do things in parallel, fully rethinking the process and reducing the final assembly line by about 10%. And we thought maybe we could do this other places.
Yeah, I mean, in a way, the constraints become part of the solution rather than a problem.
So when you think about what I'm trying to say, I really want to hammer this home. When you have a car that's about 5 meters long, and you have people working around it like we did in Model 3, and we change that to this process where we take different parts of the car, and we can do more at the same time, like we did with the Model Y structural battery pack. What you see here is us doing that on the front part of the vehicle, or the rear part of the vehicle. That means we can get more people working on the car, or robots, working on it at the same time. That means we have better operator density, less time doing nothing. I call that space-time efficiency. It has nothing to do with quantum mechanics. We can have that conversation later. But we get 44% more operator density, which means more work, less time walking back to the station, 30% improvement in space-time efficiency. And because we're not building it in and out of the car with those slow movements of those robots I showed you from production hell, when we go to automate it, it's going to be a lot easier. In the end, that will probably look something like this, where we balance parallel and series manufacturing in a way where we only do things that are necessary, with a much shorter final line, blocking a lot less of the entire rest of the factory, so we can optimize material flow using the best practices. And what that means, it's going to look something like this, where we build all the sides of the cars independently. We only paint what we need to. And then we assemble the parts of the car once and only once. We put them where they need to go. The interior is attached from a bottom-up or a top-down strategy, so there's more access for those robots and people. We aren't moving heavy objects around and doing nothing to it. And it means we're doing more work on the car more of the time. And then when we take all of these tested sub-assemblies and we put them together, we finally assemble the car only one time, putting the sides on with all of their parts to a front and rear that was already assembled, carrying the floor in with the seats, and finally boxing it out with the doors one time, just like Cybertruck. So in the end, you get the same car, but it's not going to be a Model Y.
Yeah, this is not. Yeah. This is a Model Y for illustration, not the next-gen vehicle.
In the end, what does that mean? To increase the scale and adoption of electric vehicles on the orders of magnitude that we just showed you, we have to make constraints part of the solution. It leads us to greater than 40% reduction in footprint, which means we can build factories faster, with less CapEx and more output per unit. Faster, less CapEx, more output per unit dollar. Zach's going to go into more details on this later, but it also means through this innovation and some of what my other engineering colleagues are going to talk to you about in the future, we'll reduce costs as much as 50%. This is the two-for-one concept you hear me and Elon talking about on earnings calls.
Yeah, so I think our track record proves that we can deliver the best cars, and we deliver the best cars in spite of, because of these constraints. And I'd love to really show you what I mean and unveil the next-gen car. But you're going to have to trust me on that until a later date. And I promise we'll always be delivering exciting, compelling, and desirable vehicles, like as we always have.
Have we ever not? We always do.
But what else is Tesla known for?
Speed. So with that, I want to bring on Colin, who's in charge of making our cars go fast.
And that allows us to quickly iterate through millions of possible drive unit designs to find the best one. I want to highlight one more area where Tesla really excels because we integrate work that is often farmed out. So when you are making a new product, it's not enough to think about the product itself. You have to think about how you're going to make it at scale. So at Tesla, our powertrain and our powertrain manufacturing equipment is both designed under one roof. The engineers who are designing the motor, they are in the same room as the engineers who are designing the machine that's going to put that motor together. And that collaboration pushes us from day one to design products that are not only high performance, but are really easy to assemble. So, all of this expertise that we have in the powertrain team, in hardware, in software, in manufacturing, it's going to have a major impact on our next platform. In our next powertrain, so those silicon carbide transistors that I mentioned that are key component but expensive, we figured out a way to use 75% less without compromising the performance or the efficiency of the car. And of course, we know that battery cell supply is one of the constraints on the scalability of EVs right now. Our new powertrain is compatible with any battery chemistry. And that will give us great flexibility in battery sourcing. If we want to make EVs more accessible to people, they have to be cheaper. We've reduced the drive unit cost to about $1,000. And we don't think any other automaker is even close to that number. Finally, the bigger a factory is, the longer it takes to build. If we can build the same number of cars from a smaller factory, we are going to be able to scale EV production faster. Our next powertrain factory is 50% smaller than the one that's behind me today, even though it has the same capacity. All of these improvements, I think, are going to be transformative for the adoption of EVs and our ability to scale them. There's one more thing that I want to highlight. So I talked about how we had reduced the amount of rare earth in our powertrains. And as the world transitions to clean energy, the demand for rare earth is really increasing dramatically. And not only is it going to be a little hard to meet that demand, but mining that rare earth, it has environmental and health risks. So we want to do even better than this. We have designed our next drive unit, which uses a permanent magnet motor, to not use any rare earth materials at all. So how does all this fit into the master plan? We can make lower cost products that are still efficient and compelling, and we can make them at scale. We're going to use less of constrained commodities, silicon carbide, rare earths. We're going to build them all in compact and high output factories that are easy for us to build quickly. We're going to make that easy to scale powertrains all the way up to the levels that Drew and Elon mentioned at the beginning. And this achievement, like all of the achievements that I mentioned today, it's only possible because of the incredible people on our powertrain teams. They are absolutely committed to the cause of sustainable energy, and that is why we can do what no other company can do. Thank you.